Hi, I'm Jez Siddons from Peak Electronic Design Limited here in Buxton, UK. I've got here Atlas DCA, Model DCA55, which I'd like to show you. The Atlas DCA is aimed at analysing most semiconductor components such as transistors and MOSFETs, LEDs, diodes and a few other devices, including sensitive or low power triacs and thyristors. I'm going to start with testing a few components and showing you its capabilities, as well as showing you some of its limitations, of course. So we're going to start with this TO3 device, and this still has its markings. It's a 2N3055. I'm going to connect the test leads to this device any way round. It doesn't matter what order I connect the test leads. I'm going to press the on button, and we can see that the analyzer, after it's analysed, has come up with NPN silicon transistor, which of course that's what it is. And if we press the scroll button, it tells us more information, such as the pinout. In this case, the red is on the base, the green clip is on the emitter, and the blue is on the collector. The next page shows us the current gain, and in this case we have an HFE of 90. And that's a DC current gain measured at a current through the collector of 2.5 milliamps. The base emitter voltage is also measured, and here we've got a VBE of 0.64 volts. That's measured at a different test current to the current used for measuring current gain. In this case it's measured the VBE at a test current of 4.77 milliamps. And finally, for this device, it's measured the leakage current. And for a silicon device, as you would expect, it's got such a low leakage that it's not measuring anything at all here, 0.00 milliamps. And if we press the scroll button again, it takes you back to the start. So all of those results indicate that it's a good transistor. If it was a failed transistor, then we would expect some different results, of course. So we can simulate one of those faults by shorting a pair of the leads. So this might be the case if we had a shorted junction. And if we press test, we can see here that we've got a short circuit on the green and the blue leads. Okay, so that gives us a very quick indication that there is a dead short in the transistor. Also, if we have an open junction, we may just have two of the leads that are actually connected to anything here, just to simulate that. The analyzer sees just the diode junction within the transistor, and we can see that the red is on the anode of that PN junction, and the green is on the cathode of that PN junction. And in this case, a forward voltage of 0.62 volts at a current of 4.79 milliamps. We can see from that pinout, by the way, that the blue lead shows nothing, and that's because that's not connected to anything at all. An interesting device to test is this old germanium transistor. It's a new old stock. It's AC153C and still has its original long leads. We can apply the test clips, and pressing test we will see hopefully that it is a germanium, and indeed it is a PNP germanium transistor. Most germanium transistors were PNP, although a few NPNs were made. And here we see the red lead is on the base, the green lead is on the collector, and the blue lead is on the emitter. This transistor has a current gain of 42, to test current through the collector of 2.5 milliamps. And typical of a germanium transistor, this has quite a low base emitter voltage, here 0.23 volts. That was tested with a test current of 5.22 milliamps. Again, a different current to that used for measuring gain. Now, germanium transistors do tend to have some significant leakage current. This one has a leakage of 0.08 milliamps. The leakage current of germanium transistors is very temperature sensitive. In fact, even a small increase in temperature can make quite a big difference to leakage current. And that's often seen in devices that use germanium transistors, particularly if they suffer from thermal runaway if the temperature of the device gets too hot. So we can increase the temperature of this transistor just with the warmth from my fingers, and the temperature increase of this transistor should make quite a significant increase in the leakage current, and the leakage current is measured at the point in which the analysis is performed. So if we move on to the leakage current measurement here, we can see that it's already increased to 0.15 milliamps. If we analyse again, maybe we'll see a further increase of leakage current. There you are, it's already increased to 0.17 milliamps. So this is completely normal for the leakage current of a transistor, particularly germaniums, to change significantly with temperature. And that's one of the advantages of silicon transistors, is that the leakage current is so low to start off with that any increase due to temperature is, generally speaking, insignificant. Now, because I've been handling this transistor, it's obviously got quite warm, and I guess now it's starting to cool down a little bit now I've let go of that transistor. So we should see that leakage current start to drop. So we can perform a new analysis, and if we go to the leakage current measurement screen, we can see now it's starting to fall again, and it's at 0.15 milliamps. And so as the temperature of that continues to fall and ends up being at room temperature, we'll probably see that arriving back at around 0.08 milliamps that we started off with. Here's another transistor. This is an MPSA 63, so we can attach the test leads to this part, and we can see what the DCA says. And this part is in fact a Darlington transistor, a PNP Darlington. And we can have a look at its pinout. The red lead is on the base, the green is on the emitter, and the blue is on the collector. And we can see, because it's a Darlington and it's a small signal transistor, we do have a very high gain, and in this case an HFE of 19,454, as you'd probably expect from a Darlington. That's measured at a collector test current of 2.5 milliamps, confirmed on that screen. And as you would expect from a Darlington transistor, the base emitter voltage is much higher, so here it's 1.41 volts. That's effectively two base emitter junctions in series. And that was tested with a base current of 3.93 milliamps. Again, that's a different test current to the current used for the HFE measurement. And because it's a good transistor, this has a leakage current of 0.00 milliamps. So perfectly good transistor. Here we have another TO92 style package. This is a 2N3819, and someone will recognise that as a JFET. I'm going to apply the test leads and press test. And here it's identified it as an N-channel junction FET. It is quite limited for testing junction FETs, because at the low test currents and voltages that the DCA can apply, the junction FET looks largely symmetrical about the gate lead, and so isn't able to identify the difference between the source and the drain leads. So that's shown here on this screen. The drain and the source aren't identified. However, the gate lead is identified, and here we can see that's on the green clip. No other information is shown for the junction FET, so we'll go back to the start screen. Here we have a slightly unusual TO92 style package. It's an elongated TO92. I'm not sure what the official name of that part is, but it's got markings of K941. I don't recognise that number. But the Atlas DCA will analyse this, and here we have an enhancement mode N-channel MOSFET. There are two main groups of MOSFET type, enhancement mode and depletion mode, and the Atlas DCA will support both. Enhancement mode means that the MOSFET can be switched off completely with a zero voltage between the gate and the source pins. And for this we have the pinout. The red lead is on the drain, that's in the middle, the green is on the source, and the blue lead is connected to the gate. And because it's an enhancement mode MOSFET, the gate voltage is also measured. The gate voltage is the gate voltage that causes a drain current of 2.5 milliamps to flow. So this is when the MOSFET just starts to turn on. So it's the gate threshold, here 1.52 volts. And the current through the drain is confirmed at 2.5 milliamps. Now we're back to the start. There are some components that the Atlas DCA can't analyse, and in particular triacs and thyristors that require a gate or a holding current of more than 5 milliamps can't be analysed by the Atlas DCA. Here we have a thyristor, it's part number BTW69. I'm going to attach the test leads to this device. Now this device does require a gate current of significantly more than 5 milliamps, but we'll see what the DCA says. Here it's come up with unknown or faulty component. I don't believe this is a faulty thyristor. It's just that the DCA is unable to generate the currents required to trigger this particular part. The Atlas SCR product is more geared towards the higher current requirements of many thyristors and triacs, and that is suitable for those sorts of parts. The Atlas DCA is more suitable for parts that require much lower currents to trigger. As an example of a sensitive gate thyristor or triac, we've got one here. This is an S0402, and we can attach the test leads to that. And here we have a sensitive or low power thyristor. And it gives us the pinout. The red is on the gate lead, the green is on the anode, and the blue is on the cathode. Now for thyristors or triacs, it will only identify the pinout, it will give you no further information. So we get back to the start by pressing the scroll button here. For two leaded components, you can use any pair of the three leads. So here we have an LED, of course. We can just pick any pair of the leads, so let's have red and blue. For no reason at all, you can pick any pair of leads and put them on in any order. So as we press the test button, you'll be able to see the current going through the LED as it analyses it. And as a result of that, it's come up with a message LED or diode junctions. So of course this is an LED, and we can now see the pinout. We have red on the anode, which is positive. Green is not connected to anything. And blue is on the cathode, that's a negative. And it's measured the forward voltage drop of this LED. In this case we've got 1.78 volts at a test current of 3.5 milliamps. Now we can test other types of two-leaded components, and in this case we have a rather nice bicolour LED, and again as we press the test button you'll be able to see the current flowing through the LED briefly, and it's found both LED junctions within that package. So it says 2-terminal bicolour LED. For a 3-terminal bicolour LED, the third lead is used, of course, and so it will identify that uniquely as well. So because it's measured both the LED diodes within that package, it's going to describe each one in turn. So the first diode, D1, we have red on the anode, so we have positive on the anode, and blue on the cathode, negative. And that has a forward voltage drop of 1.94 volts at 3.35 milliamps. Then it will tell us about the second diode in here. And this 2-terminal bicolour LED has two LEDs wired back to back. So we can see, of course, that the anode and cathode are the other way round for the second diode. Red is on the cathode, negative, and blue is on the anode, positive. And that has a lower forward voltage drop of 1.72 volts. And that's typical of two LEDs which are of different colours. We would expect the red, for example, to have a lower forward voltage drop than the green. So we've been able to identify the polarity of this device for each colour, the red and the green parts of this bicolour LED. And that was measured at a test current of 3.59 milliamps. Then we're back to the first screen again.